Measuring the success of a cognitive theory comes down to one metric: its ability to generate new, effective instructional procedures. Imagine navigating a labyrinth where you are forced to stare only at the exit. You might move quickly, but you will repeatedly hit dead ends, entirely missing the actual layout of the walls around you. Standard educational design operates on a seemingly obvious assumption. To learn efficiently, novices require clear, specific goals. 3 decades of randomized controlled experiments in cognitive psychology reveal a different reality. Giving novices a highly specific target frequently impairs their ability to form long-term memories of how a system works. Look at this comparison. On the left, a standard high school geometry problem asks a student to calculate a single specific angle, angle ABC. On the right, a goal-free variation simply asks them to calculate the value of as many angles as they can. The geometry itself hasn't changed. The problem space is identical. The only variable altered is the removal of the specific target. Replacing that target with an exploratory environment forces the brain to abandon a common cognitive bottleneck known as means-ends analysis. Stripping away the finish line lowers the extraneous cognitive load placed on the learner, allowing the brain to focus on the long-term memory structures required for true expertise. This suggests a hidden tension in the classroom. The mental effort required to reach a specific destination may actually prevent a student from understanding the path they took to get there. When you give a novice a specific target, their default strategy is means-ends analysis. They look at the goal and try to work backward to the starting conditions. This illustrates the capacity limits of human working memory. First, the learner holds the initial problem givens in mind. Simultaneously, they lock on to the ultimate goal, actively calculating the distance between where they are and where they need to be. Finally, they have to load various mathematical operators into memory to try and bridge those gaps. Cognitive load theory defines this chaotic overlap as high-element interactivity. The brain is juggling too many intersecting pieces of information at once. Often, this heavy processing works. The student successfully works backward and solves the immediate problem. But because their working memory was entirely consumed by managing those overlapping variables, they lack the spare capacity required to actually remember the sequence of steps they just took. Means-ends analysis produces short-term performance, but the resulting cognitive load leaves no room for long-term learning. The structural rules of the problem cannot be processed and stored while the mind is occupied with the search for a solution. This changes the moment the specific target is erased from the instructions. Without a specific endpoint, the student cannot work backward. They have no anchor for a means-end strategy. Look at the working memory cluster now. The heavy cognitive demands of tracking the goal and calculating differences simply disappear. The learner is forced into a forward working strategy. They evaluate the current state and calculate the single, immediate next move. This dramatic drop in mental strain aligns with the narrow limits of change principle, ensuring working memory is not overwhelmed. That newly freed capacity is instantly reallocated. The brain begins building local structural links between the variables it is manipulating. Linking these sequential states together allows the learner to construct a reusable framework, or schema, and store it permanently. By removing the pressure of a finish line, the instructional design organically aligns with the biological constraints of human working memory. This theoretical model is backed by decades of data, notably starting with Owen and Sweller's 1985 trigonometry experiments. This chart illustrates the acquisition phase of their study. Given the exact same time limit, students assigned goal-free problems calculated twice as many sides as the goal-specific group, while making significantly fewer errors. The post-test results reveal the impact. When both groups were later tested on conventional problems with specific goals, the goal-free group was 5 times as accurate and demonstrated superior structural transfer to new types of problems. Researchers Vollmeier and Burns proposed dual space theory to explain the depth of this knowledge transfer. Their model visualizes 2 distinct psychological spaces a learner can inhabit when interacting with a complex system, the instance space and the rule space. Assigning a specific target traps a learner entirely in the instance space. They manipulate variables in a brute force attempt to reach the required state, ignoring how the system actually works. Goal-free exploration pushes the learner into the rule space. It encourages active hypothesis testing and maps out the underlying causal relationships between variables. By setting a specific goal, the instructor shifts the learner's entire psychological focus, often moving them away from comprehension and toward rote execution. The goal-free effect operates under strict boundary conditions. It is highly effective, but it is not a universal pedagogical fix. Problem space complexity determines when goal-free instructions succeed. The effect thrives in constrained spaces, like geometry, where a limited set of operations means every forward move holds educational value. In unconstrained spaces with infinite possible moves, aimless exploration wastes cognitive load on irrelevant tangents. Developers face a structural conflict, balancing the necessity of testing performance goals against the biological limits of a novice's working memory. To implement this correctly, instructional designers must audit their materials to find transformation problems where novices instinctively rely on means-ends analysis. At these choke points, the fix is mechanical. Erase the specific target from the prompt and instruct students to calculate all unknowns. To rapidly accelerate a novice's expertise and teach them the underlying rules of a complex system, you must initially remove the finish line.